In this lecture, let's understand preempt priority and subpriority. Before understanding this, let's understand what happens if two interrupts of the same priority hit the processor at the same time. Now the answer is, in this case, the subpriority value of the interrupts will be checked to resolve the conflict. An interrupt with lower subpriority value will be allowed first. That leads to our next discussion. What is preempt priority and subpriority? These are the terms used in priority grouping. I will explain that in a moment. When the processor is running interrupt handler and another interrupt arrives, then the preempt priority values will be compared and interrupt with higher preempt priority will be allowed to run. Subpriority value is used only when two interrupts with the same preempt priority values occur at the same time. Remember that. In this case, the interrupt with higher subpriority will be handled first. That means subpriority is used to resolve the conflict only when two interrupts with the same preempt priority values occur at the same time. Based on preempt priority and subpriority, we have priority groupings. There are various priority groups, and by default in ARM Cortex-MX processor, the priority group is 0. Priority group depends on the usage of this interrupt priority register. It's very simple to understand. Let me explain. As I said, the default priority group is 0. In this case, bit 1 to 7 are considered as preempt priority and bit 0 is considered as subpriority. If there are two interrupts having same preempt priority values occur at the same time, then this bit will be used to resolve the conflict. That's it. Suppose if the priority group is 5, then 7 to 6, that is, these two bits are used as preempt priority and all these bits are used as subpriority. In this case, we have got only 4 priority levels because there are only 2 bits allocated for preempt priority. We have 4 different priority values or priority levels like that. This is the concept behind priority grouping. By the way, you can control the priority grouping by changing the value of this register, application interrupt and reset control register, which is part of SCB. You have to modify these bit fields. By default, this is 0. Let's take up some case study. What happens when the priority group is 0? When the priority group is 0, as per the table, we have preempt priority width 7 bits. So up to here, these are preempt priority 7 bits. That means 128 programmable priority levels. But only 3 bits are implemented. Out of these 7, these are not implemented. So we left with only 8 programmable priority levels. If the priority level register looks like this. Subpriority width is equal to 1. This is a subpriority width. That means 2 programmable subpriority levels, that is 0 or 1. But bit 0 is not implemented, so no subpriority levels. In this case, we have no subpriority levels, only preempt priority levels. What if priority group is equal to 5? Preempt priority width is equal to 2 bits. This is preempt priority. That means 4 programmable priority levels. That's true. Subpriority width is equal to 6. Since only 1 bit is implemented, these are all not implemented, only 1 bit is implemented, only 2 programmable subpriority levels. Like that, you have to understand. What if 2 interrupts of the same preempt priority and subpriority hit the processor at the same time? That's an interesting question. In that case, interrupt with the lowest IRQ number will be allowed first. For example, let's say the timer 2 interrupt and the I2C1 interrupt happens at the same time, and if both of them have same preempt priority and sub priority values, then interrupt with the lowest IRQ number will be allowed first. Here the IRQ number of timer 2 is 28 and the IRQ number of I2C1 is 31. Timer 2 will be allowed first. By default, that will become the high priority interrupt. That's about priority grouping. That's it from this lecture. Let me know if you have any questions, and I'll see you in the next lecture.